วัสดีค่ะยินดีต้อนรับทุกท่านนะคะกลับเข้าสู่ IAEA Expert Mission Strengthening Optimization in Radiological Practice นะคะอาทิตย์นี้เป็นอาทิตย์ที่11ของมิชชั่นนี้แล้วนะคะซึ่งอาทิตย์นี้เนี่ยเราจะมาพูดถึงในเรื่องของ dose metric แล้วก็setting dose alert level ของ mammogram นะคะโดยเราก็ยังได้รับความอนุเคราะห์จากผู้เชี่ยวชาญของ IAEA นะคะดร. Sam Brady จาก Cincinnati Children's Hospital ที่จะมาเล่าให้เราฟังถึงในเรื่องของ dose alert level แล้วก็ dose metric ของ mammogram นะคะ Good evening Sam nice to meet you again and welcome back to the expert mission we are almost done this week is week 11 of 12 that we are going to talk about, we're going to follow from last week. So last week, we're talking about the mammogram optimization and also the metric. And this week, we are going to focus more on the dose metric and also how to set up the dose alert level. So it's your time. Mm-hmm. Oh, I need to unmute you again. Yes, sorry. Hold on. Hold on. Oh, where is? Yes. Mm-hmm.
Hello.
Hello.
Now you can hear me.
I can hear you now. Now you can talk. Yep.
I can just talk with my hands the whole time. All right. Well, thank you. I'm glad to be back. Yeah, it's amazing. It's been 11 weeks. We've been going strong.
Believe it or not, almost 3 months. Yeah.
So 11 weeks and we're on session 19. So this has been quite the ordeal. And I'm very, very glad for every one of you that have stuck with us this whole time. We've talked about all of the different modalities. Today is the second discussion on mammography, which is the last modality that we're going to talk about. So obviously, as we discussed a while ago, next week will be just a wrap-up session where we'll kind of summarize a lot of the points that we talked about. So as Tanya mentioned, last week we talked about image quality optimization in mammography. So today we're going to focus on dose. The first session will be on the dose metric. So how do we calculate dose in mammography? And then the next session in a little bit, we'll talk about how do we optimize it. So it's actually very simple. In mammography, there is one dose metric. There is one way to calculate dose that we typically use for diagnostic reference levels. It's the way we've been doing this for many years, for several decades now, and that is the mean glandular dose. Most publications still call it MGD, or mean glandular dose, but the IAEA and almost all international societies now list it as D sub G, which is glandular dose. So throughout this talk, I am going to refer to mean glandular dose as D sub G, just to be in line with the IAEA. So to calculate mean glandular dose, we need to know air kerma. And that's air kerma at the surface, the entrance surface of the breast. So as the mammography unit is usually going to be craniocaudal or medial lateral oblique, we're talking about the exposure dose at the top point or superior aspect of the breast. In a more recent time, in the last couple of years, there has been a new dose metric proposed in mammography. It's called the average absorbed breast dose, or 2ABD. And we'll talk about why this is now being offered. When we look at dose reference levels, there are no dose reference levels out there right now for 2ABD. So everything that you guys are doing in Thailand for your DRLs, we're still talking mean glandular dose. But we're going to talk about 2ABD because 2ABD is actually probably at some point going to replace MGD, or excuse me, mean glandular dose. It's just it's a different type of, or a different way to do the same thing. Here we go. Now we should just talk briefly how in literature you'll also see people refer to effective dose for breast imaging. Obviously, we've said this many a times, but we do not use effective dose to calculate DRLs or publish DRLs. But I have one slide. I'll talk a little bit about how we calculate effective dose, or how we use effective dose in mammography. So mean glandular dose, because it's still the main metric for DRLs, we're going to focus probably the majority of our talk today on this metric. This metric like I said, this metric has been around for wow, it's going on a little over 20 years. No, a little over 30 years now. The very first publication that came out was in 1990 by Dance and his colleagues. And this, our very first publication, obviously some 30 years ago, was based on film mammography. So it only looked at the common target of moly or molybdenum and rhodium, and the common filters, which was molybdenum also and rhodium. So the common combinations of the target and filter were moly-moly, moly-rho, or rho-rho. So those three major or unique combinations of target and filter were used back in film days. And so when you look at this publication, it only refers to that old way of doing imaging, although there's still one vendor today that uses those same combination of target and filters. Dance, however, came out about 10 years ago with a updated publication where he included a new way to, not a new way, but he added new lookup tables for his original empirical method of calculating glandular dose. And now he includes all the brand new targets, such as tungsten, and their new filters, such as rhodium, tungsten rhodium, or tungsten silver. So the second most common method is the Wu method. And this came out about 4 years after the very first Dance method. And once again, as you can assume, back in 1990s, it was all film-based. So it was the moly-moly, moly-rho, rho-rho. And John Boone came out about 5 years after Wu, and he published his version, which built off of Wu. But because Wu only did moly-moly, moly-rho, and rho-rho, Boone, he added tungsten, rhodium, and tungsten silver to that option. So when we talk about today's way to calculate mean glandular dose, there's really only technically two ways to do it. There's the Dance method and there's the Boone method. But the Boone method is based off of the Wu method. So I know it sounds complicated, but it's all there. So what do we need to know to calculate this methodology? So the mean glandular dose, you need to know the breast thickness, the amount of glandularity in the breast. So we oftentimes talk about the standard model being 50% glandular tissue, 50% adipose or fat tissue. Obviously, we're going to talk about how in a little bit later in this lecture that 50-50 standard breast dose, or standard for breast glandularity, is kind of mythical. It really doesn't exist. So obviously we need to figure out a way to calculate different types of glandular. So for women that have less glandular tissue versus women that have more glandular tissue. But you need to know breast thickness, glandularity. You need to know what the X-ray spectrum is of the system. So you need to know what the target and filter is, and you need to know what the beam quality is, or the half value layer. If you know these four things, you can calculate the mean glandular dose. And you could do this by hand, but it's very difficult. So what ended up happening is you had the Dance, the Wu, and the Boone method that they published based on a bunch of Monte Carlo calculations. They published a bunch of tables. And so if you know what your X-ray spectrum is, so you know what your target and filter is, and you know what your half value layer is, and the breast thickness and assumed glandularity, you can look up a correction value and you can make the calculations. So when it's all said and done with, it's very important to understand that we keep saying mean glandular dose, but it's actually a dose estimate. We don't really know what the dose is to the breast being imaged. It's a model. The calculation is based on a breast model. It's not actually patient-specific dose, which should be no surprise because there's no patient-specific dose in CT, there's no patient-specific dose in fluoro, there's no patient-specific dose in X-ray. So you would assume that there would be no patient-specific dose in mammography. So we always talk about patient dose, but we actually don't know the specific dose. We can get real good estimates, and there's no reason why those estimates shouldn't be applicable to patient populations. But when Jane walks in and, you know, someone gets their mammogram, we don't actually specifically know what the dose is to that breast. So let's look at the two major methods, the dance method and the Wu-Boon method. The dance method is probably the most common. You'll see this in publications whenever you read about mammography. And the way that he developed this is you take the air kerma as measured at the entrance surface or the upper part of the breast tissue, and you need to correct for the amount of glandularity. This G factor assumes a 50% glandular, 50% fat breast model. But we know that every breast that gets imaged is not exactly 50-50. And so we have to take into account for that particular breast being imaged in that scenario, in that moment, we need to then correct for however much glandularity is in that breast in that image. And that's what C is. C is an estimation of the glandularity in the image of the imaged breast. And then S is that spectra correction. Remember the half value layer, which is dependent on the target filter combination. Excuse me. So then Boone, as we've already discussed, he basically modernized Wu's calculation to move beyond just Molly, Row, and Row, which are the only scanner out there on the market now that you can buy modern. So maybe you have older scanners that still do this, but more modern scanners. The only modern one out there that could use the Wu method is GE. And so theirs is slightly different. Basically, you still need to know the air kerma at the upper entrance surface of the breast, but then there's just a single value. Instead of the CGS correction coefficients, now it's just this D sub GN. And that value is, once again, a value you can look up in a lookup table. So Boone provided all of these empirical equations. So you could actually use these equations if you wanted to create your own calculation model, your own software. You have these equations that you could build into it. The equations are based off of breast thickness and the machine half value layer or the beam quality. And there are equations based off of assumptions, such as these equations you see here are made for a 50% glandular, 50% fat breast model. And it's very important to recognize, and we'll talk about this a little bit later, that all of these standard breast models assume that there's the skin layer, that there's a 5 millimeter layer of fat before you get to the glandular tissue underneath. Every breast model assumes this skin, fat, glandular type model. And I know you guys have seen enough mammograms for those of you that look at them to know this breast model is not actually a traditional or typical breast that you would see. Now, I'm not saying there isn't a breast out there that has a 5 millimeter fat layer, but they all come in different shapes, sizes, and mix, glandular fat mix. But that said, once again, this is a dose calculation for a standard model. And so you can go in, you can look at all these tables depending on your combination of target, filter, and whatever assumption of glandularity. So this table I just simply took a screenshot of is for 100% glandularity for the tungsten, rhodium, target, filter combination. And then you would just know what KV you used. You would know the half value layer for that system. And then depending on how thick the breast is, you'd pick a number, let's say this 96 value, and that's the value you would multiply to the air kerma to get your mean glandular dose. A publication that came out 2017, so only 3 to 4 years ago. This isn't an old one. And what Suleiman and his colleagues did is they looked at the reported mean glandular dose, the value that the machine tells you. So it's written down somewhere on the screen or part of the metadata. It's the machine reported mean glandular dose compared to the value that these scientists actually calculated using the dance method, the Wu method, or the Boone method. So the manual calculations are on the y-axis. The machine reported values are on the x-axis. Here you can see on the left, you have GE. On the right, you have Sectra, which is now Philips. And then in the middle is Fuji and Hologic. And the dashed lines going here at the 45-degree, and every one of these plots is quote unquote truth. If the machine reported a number that was exactly the same as what was calculated by hand, then it would be a one-to-one correlation or perfectly accurate, 100% accurate. So anytime the trend lines deviate from this dashed line, that tells you how much the system values are different than truth. So you can see here, there's a couple things going on. GE uses the Wu method because, Wu is only good for Molly, 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 row, or row, row. And you can see for two different types of GE scanners, one is very accurate and one is overestimate. The system overestimates. System underestimates. If the line is above the dashed line, it underestimates. So the machine says it's 4 milligray. The reality is it's actually 6 milligray. So if it's above the line, it underestimates. And then you come over here, you can see, for example, the Boone method being used down here in Hologic is actually fairly accurate, but it's not very precise. You can see how there's a lot of variation, a lot of spread in the data, whereas basically all the other plots you see here are very tight to the dashed line. And then you see here the Sectra, the Philips, they're pretty accurate, although this Philips system has kind of this weird little deviation up here for whatever reason. So what you see here, just take a big step back and look at this. Every machine reports slightly differently the dose. Every machine has a different accuracy, and every machine has a different precision. So that's just a big picture here. When you look at all of this together, Solomon reported that there is a range, a difference in reported doses anywhere from 24.24 milligrays underrepresented or underreported to 0.36 milligrays overrepresented or overreported, which is about an 18% spread. And here's just some actual numbers. These are the mean or the average mean glandular dose values. And it's broken down by the system output and then the manual calculation using dance, Wu, or Boone technique. And I'm going to talk about that in a moment. But the question that I ask is why? Why a plus or minus 18%? Why such variation from vendor to vendor to vendor? Now, each vendor has adopted their way of calculating things. So Philips or Sectra uses the dance method. GE uses the Wu method, which is no surprise. Hologic, Boone, Fuji uses dance. But the way that you calculate and make assumptions based on the glandularity of the breast being imaged at that moment is unknown, or as listed as proprietary. So therefore, the vendor is not telling the scientists or telling anyone how they make those assumptions. So a lot of the variability in how we calculate mean glandular dose is based on this idea of how we estimate glandularity in the image and how we correct for that for the dose calculation. So let's just look at the data a little bit closer. So a couple of things you would assume. You would assume that if the system, for example, Philips, which uses the dance method, you would assume that their output value would be fairly similar to a manual calculation using the dance method, which in this case, it is, in these two Philips units or Sectra units. And if you calculate them using a Boone method, in this case, the Boone method is actually pretty different. In this case, the Boone method was actually pretty accurate. And then GE used the Wu method. Interestingly enough, the GE output value, 1.42, does not match the Wu method. It actually matches very closely with the dance method. So it's kind of a little strange, and the Boone method's much different. And then you would expect the ones like we've said here, Hologic, for example, uses the Boone method. So you'd expect their output of 1.73 to be identical or nearly identical, but they're not. And Fuji uses dance. You would expect these to be identical, but they're not. In fact, in this case, the Fuji matches very closely with the Boone method. So there's just a lot of variability built into all of this. You just have to understand that when you get the data, especially when you're doing the dose, the diagnostic reference levels, when you collect all this data, that there is actually going to be a spread in accuracy. There's going to be a spread in accuracy if you actually physically calculated it. If hospital A sends calculated data in, well, there's going to be a measured spread in data, measurement error. And then there's just intrinsic error based on the way that the mean glandular dose is calculated. So how does this compare to other modalities? You might be thinking this is not good, right? 18% spread. Well, in fluoro, remember, the error curve measured at the international reference point, the IRP, that is actually only required to be within 35%. So not quite double, but you know, the values that you measure on a fluoro system can be significantly different than what you actually physically measure using an ion chamber. CTDI, vol, or the volume CTDI and CT, can be upwards of difference of 20%. So breast dose, mammography doses are actually not too far off. In fact, they're actually doing pretty good when you put it in comparison of the other machines out there when we're calculating their and collecting their values, their dose metrics, CTDI, vol, and error curve at the IRP when we do DRLs. How do we use these values? Well, you have to understand, because there is some inherent variation when you compare one machine to the next machine to the next machine, you have to understand that obviously machine to machine comparison should be pretty accurate. So we can use these as dose audits, and then we can use them to establish diagnostic reference levels, of course, which is what we're working on. And so we'll talk about diagnostic reference level at the end of my second talk, but that just put that in the back of your mind. It's probably helpful to collect all that data, and you'll have your national diagnostic reference level, but it would also be helpful statistics wise if you have enough statistics to break it down by vendor type. And we'll talk a little bit about other ways to break it down, but there is a little bit of variation from machine to machine to machine. And so if one hospital uses all Sectra, but the data for the diagnostic reference levels was collected primarily for like a GE or a Hologic, then those numbers are going to be obviously different. But when you say a diagnostic reference level is, say, of 2 milligray, but this Sectra is a little higher, their value actually might be not that bad. It's just reporting differences. So, but we'll talk about that in the next talk. So we've been talking about here full field digital mammography, or breast to view, CC, MLO, craniocaudal, medial lateral, oblique, when we're doing full image standard dose. The other way we do mammography is tomosynthesis, where we do the sweep over a limited angle over the breast for either a craniocaudal or a medial lateral oblique. So how do we do not organ dose, but mean glandular dose for this? In the dance method, it's the exact same thing with one more term tacked onto the end. T, capital T, is called the tomo factor. And the tomo factor takes into account the individual tomo projections and weighting factors for each projection. Obviously, certain projections are going to incorporate only a certain amount or dense or thickness of the breast, whereas others will have different. So we have to take into account the sweep effect. So let's look at the tomo factor. One of the beautiful things about the tomo factor is it is not dependent on glandularity. And it is dependent, of course, as you would expect, the half value layer. So it is vendor specific. So when we have lookup tables, we will need to have different lookup tables for each vendor and for every target filter combination out there based on KV. You can see here by this curve, it's also dependent on tomo angle. So some systems may only do 15-degree sweeps. Some may do a full 30-degree sweep. And you can see how this factor, how it changes as a function of angle. So the tomo, as it sweeps over, may change. This theta may be smaller for some and larger for others. And then, of course, we need to know what the breast size is. The breast thickness is going to change as a function of angle as you sweep over it. All of this is taken into account. They've done a lot of simulations and publication based on those simulations. And so now, based on breast thickness and the type of machine you're using, you can go look up these T factors. So you still need to know the error kerma and the G, the C, and the S. But now you can add to that just one more lookup table that you can find and tack that on to calculate mean glandular dose for a tomographic sweep. All right, I mentioned at the very beginning, mean glandular dose is the primary dose metric for mammography. We've been using that now for 30 plus years. But in the recent last probably 5 or so years, there's been a lot of talk about this 2ABD metric. So let's talk about what it is and how it's slightly different than the other mean glandular dose calculations we've been talking about. So here's the equation. It might look ugly, but it's actually fairly simple. Really, all we're doing here is we're integrating, or we're summing over the thickness of the breast based on the entrance air kerma coming into the breast and the attenuation factor, or the amount the breast attenuates the radiation. And then we normalize or divide that by D, or the depth, or excuse me, not the depth, the thickness of the breast. And the nice part about this attenuation coefficient right here, this attenuation portion of the calculation, is that the attenuation coefficients depend on KV, MAS, so the MA times time, or MA times S, and the target filter combination. All of these values, those 3 values right here, are values you can look up in the DICOM metadata. So you take a picture, a MLO or a CCC, a CC image, and that image will come across to PACS, and in the metadata, in the header, you will find the KV, the MAS, the filter target combinations. And from that, you can look up the mu sub n, En. And then, of course, we know breast thickness based on the compression. So what I'm trying to say here is when you look at this equation, here I did the math right here. You just integrate over. All you need to know is the error kerma. You need to know what the attenuation coefficient is based on KV, mass, and the target filter, and the breast thickness. All of these values are readily available in the header in the DICOM metadata, except for the error kerma. But based on the values given in the metadata, we can calculate error kerma at the entrance point, because we know what the source to image distance is. We know how thick the breast is, so we know where we're measuring this in space, and we know what the output is based on KV and MA. So we can actually calculate the error kerma as it enters the breast. And when you look at across all vendors for all different thicknesses, so every different place along the imaging chain, the measured error kerma was almost nearly identical as the calculated. So that means everything we need to calculate the 2ABD can be found in the DICOM metadata. And that is why 2ABD is becoming a very powerful dose metric, and why I think at some point in the near future, 2ABD is going to replace the mean glandular dose calculation. 2ABD can be calculated based on DICOM data. D sub G, mean glandular dose, cannot. We still need to make a bunch of assumptions, and we still need all those lookup tables to calculate mean glandular dose. So it's not that efficient. So if we have a lady come in to get her mammogram, she gets the image. The image could then, from the metadata, from the DICOM data, calculate the dose, the average dose of the breast. If you want to do the mean glandular dose calculation, you have to go look up a bunch of you have to go and use the values from the machine and look up a bunch of correction values, the G, C, S, and if it's a digital breast tomosynthesis, you need to look up the T. So it's not very efficient doing it that way. But one of the beautiful things about 2ABD, if you look back at this equation, there is no correction for mean glandular dose. And remember, in the D sub G, the mean the assumption or the prediction of glandularity was probably the thing that caused so much variation. So therefore, not needing to know how much glandularity there is in the breast, we can actually get a little bit more precise calculation for the average organ dose to the breast, or the average dose to the breast. All right, when you look at the calculations, so the measurement uncertainty, meaning this 2ABD is less than 0.1, so it's less than 10%, which is, it's on par, right? We mentioned the D sub G was 18%, so it's a little bit better. At least it's not worse, so that's good. All right. Now, let's talk a little bit about effective dose. I really, frankly, only have one slide on this, and that's because we can't use effective dose for DRLs. But oftentimes you see this used quite a bit in publications. And the reason for that is, at least as people think about this, when you look at the 4 most sensitive organs and tissues in the body, breast is one of them. And it's got a mean tissue weighting factor of 12% or 0.12. And so because breast tends to be a little bit more sensitive, breast tissue is more sensitive to radiation. And what I mean by sensitive, that means there is a correlated risk to cancer at higher doses, of course. Then they almost always report effective doses for breasts. But you need to understand, when we calculate effective dose is the average of both breast dose values. So you would get the average D sub G for breast, left breast and right breast, and then you would multiply that average by 0.12. Now, we don't always image both breasts, maybe on a diagnostic performance. If you go in for your screening mammography, there's something suspicious on the right breast, the lady comes back, the woman is only imaged on the right side. Obviously, you can't average 2 because there's a 0 value here. So when you calculate effective dose for one breast, you have to take the value D sub G multiplied by 0.12 and divide it by 2. All right, so everything we've been talking about is based on the standard breast dose model. So let's talk a little bit about that breast dose model. First thing is first, we assume that the standard breast dose model has a compressed thickness of 4.2 centimeters. And so we use a phantom to mimic that thickness. And then we assume that the breast is made up of equal parts fat, 50% fat, and 50% glandularity. I call it the mythical 50-50 breast. We're going to talk about how many women out there have 50% glandularity and how many of them have 50% adipose. And then I'll leave it to you to make the assumption, or to answer the question, is the 50-50 breast dose model a accurate model to be used for women? So the phantom itself that you can go buy or you can make if you're really interested in, it needs to be made of either acrylic or BR12. BR12 is a soft tissue mimicking phantom. It's plastic. But it tends to be a little less dense than acrylic. You typically want to get these in slabs of 2 centimeters or 2 centimeters, so you can build up different thicknesses. Obviously, you'd want to be able to get 4.2 centimeters, but there are different breast thicknesses, and so we'd want to be able to mimic all different breast thicknesses. Here in the US, we typically use what's called the ACR breast phantom. I imagine you guys probably use this too, because the IAEA has adopted the use of this breast phantom also. This breast phantom itself has image quality targets embedded in it. And so we typically image the phantom to measure or get an estimate of the overall image quality in the system. But we use the phantom in this situation to also measure the dose to the breast. So the phantom itself mimics a 4 to 6 centimeter thick compressed breast. And we place the phantom on the detector over top of the AEC sensor. Obviously, we put the compression pedal in the field of view, and then we take the ion chamber here, you can see right here, this circular object, we take this ion chamber and we place it so it is in the same plane, so it's up here parallel with the surface of this phantom. The phantom itself, because it's over the AEC, will cause the system to it'll cause the system to use a certain amount of exposure commensurate with a 4 to 6 centimeter thick breast. And the ion chamber, of course, will then measure that dose with respect to however much MAS is being used to image this phantom. We place this chamber specifically about 4 centimeters from the chest wall, or this edge of the detector. And then, like I said, we keep it so it's level with the top of the imaging phantom. All right, we obviously, I already talked about the compression paddle. Here we go. We obviously need to use clinical protocols. So you would go in based on your 4 to 6 centimeter patient protocol. You would set the KV and you would let the AEC then run the MAS. The system would pick the target and filter based on the KV you've established in the protocol. And then you'll make multiple measurements, usually 4 or so, and then you average them together, and that will be your exposure for this breast phantom, or X, your exposure value X. So now we need to calculate or look up a correction value F to scale the exposure value, because it's obviously being measured here in air, and we need to make that an actual estimate for mean glandular dose. So how do we do that? These conversion factors are dependent on the half value layer, or the beam spectrum, or quality, which is dependent on KV, target, and filter combinations, and our assumption of breast composition. Is it going to be 50-50? Is it going to be 25% glandularity, 75% fat, etc.? And then obviously the breast thickness. Of course, the breast thickness using this phantom is standard, 4 to 6 centimeters. Here's an example. We just do a simple math, a simple example to show you how to do the calculation. If you have a protocol that uses a KV of 26 and your MAS, your AEC would drive the system to produce 100 MAS, you would need to know what the half value layer is for your 26 kV exposure. And if it's 0.33, as in this example, and you know that 26 kV here is the correction value, F. It's 168 millirads per R, which is equivalent to 1.68 milligrays per R, or Rankins. We've made our measurement using the ion chamber, so we know that it produced 1.02 Rankins. So we multiply these two together. Our estimate for the mean glandular dose is 1.71. So D sub G is 1.71. So we measure using our ion chamber, and then based on our half value layer in KV, we look up a correction value. So it's pretty straightforward. Just a word, there is a newish, I should say, ACR Phantom. It's actually been out for, I think it's getting close to 10 years now. It's been available. So I don't know which Phantom you typically use. Most people still use that. A lot of people still use that small one. But this new Phantom is actually a really nice Phantom because it covers the full field of view. So when you do your image quality assessments, you don't have a teeny Phantom inside a big white field. You can actually, because the Phantom now covers the full field of view, the dynamic range of the system is better. And also, because we're using digital imaging, digital detectors now, we needed a Phantom that had smaller masses and less contrast in their targets, so that we could actually truly see how good the system is. The older square, smaller Phantom was developed back in the day when we did all mammography was film. So the big problem with this Phantom, it's still the same. It's still 4.6 centimeter. It mimics a 4 to 6 centimeter thick breast, but it covers the full field of view. So you can't place your ion chamber next to your Phantom to make your measurements. So how do we do this? Well, you take the Phantom, You place it in there, you situate it. Once again, the wax insert is over the AEC. You got the compression paddle in the field of view, and you acquire an image, and you use your clinical protocol, whatever it is, so you know what kV it is. You'll know what the half value layer is. You write down the technique factor. This phantom exposure gave me, let's say, 26 kV and 100 MAS. So once you've written that down, you take that phantom out. A good practice is to place like a sheet of copper or some kind of, I don't know, like lead or something, just to cover and protect the detector. And then you place your chamber, your ion chamber or your digital probe, once again in the system over the, centered over where the AEC chamber is. You got the compression paddle, of course, in the field of view. But you can't use the AEC because you got a big copper plate here. So what you do now is you set it to manual mode and you use the technique factor that you had just acquired based on this phantom up here. So that, in my example, the 26 kV, 100 MAS. Now your ion chamber, your digital probe will measure the exposure or the output based on that technique factor that we established based on the phantom thickness. Same process, you still have all these lookup tables to find your F value based on kV, half value layer, and once again, you can pick it for all breast thicknesses. You can do your 4 or 4.2 centimeter, 5, 6, 7, 8 centimeter thick. Here you can see this is simply a screenshot of one of the lookup tables. This was for 100% glandularity. You could get the same would be true. You would see a similar looking table if it was 50-50, or if it was 25-75 or 75-25, whatever that combination of breast glandularity versus breast fat. Now, once you have 3 or 4 of these lookup tables, you can actually put them in Excel, in an Excel spreadsheet, or if you like to use, Python or MATLAB or R, however you like to do your software programming, you can create it so that you can interpolate between all of these values. So now you could figure out what a 4.3, 4.5, or a 5.7 thick breast is for any percent glandularity for any kV combination. And you'll be able to do mean glandular dose for any protocol you could ever possibly think of, because there's obviously a huge range of breasts out there, breast composition, breast thickness. All right, and then obviously there's all kinds of different targets and filters depending on the machines you have in your hospital. So let's talk a little bit about the expected breast dose variation. So we've been talking quite about this variability built into the fact that as humans, we all come in different shapes, different sizes. So we know there are some fundamental truths. First, smaller breasts tend to be more glandular. So in this publication here, you look at the mean breast thickness as it trends smaller. So here's a 2 centimeter breast, 3 centimeter, and this is compressed, of course. You can see the glandularity tended to be in this patient population higher. Whereas a thicker breast, usually out towards 8 centimeters, was much less glandularity by volume. And we just know as the breast tends to get bigger, it tends to be bigger based on the fat volume, and glandularity will tend to be consistent. We know for an equal thick breast, if that same thickness of breast, let's say 4.2 versus 4.2 centimeters, if one of those has a higher level of glandularity, say 30, 40, 50, 60%, we know the system will need to use more MA or MAS to penetrate the breast to create the image. And that is because glandular tissue is more attenuating than fat. That's why it looks white on the image compared to the fat, which is darker black or gray. And then we know, of course, the more we compress the breast, the thinner it gets, the less radiation we need to use to penetrate it, less photons. And that's unfortunately why we put all these women through the horrible experience of compressing their breast. But you see here on these plots that the thinner they go, the lower the dose is. And the thinner they go, the less kV we need to use, which is a good thing for image quality, because as kV goes down, contrast goes up. So when we look at this variation across the general spectrum of compressed breast thicknesses, we see that there is basically a plus or minus a factor of 2 dose. So it varies quite a bit in radiation dose across this small, what you would probably consider a small spectrum of say 2 to 8 centimeters. But within that same spectrum, you'll see the dose change by a factor of 2, can be up to a factor of 2. Now that ACR phantom that we use, that is pretty standard. Internationally, the IAEA, here in the US, of course, in Europe, they have theirs too. But, whoops, that 4.2 centimeter breast, if you look at 4.2, when you compare that to the patient population out there, that actually, 4.2 centimeter breast, actually only represents about a 40% glandularity. So the phantom itself mimics 50, but what we're saying here is the patient population for a 4.2 centimeter breast is actually on average only 40% glandularity. So you see an example here of where the standard breast model, it doesn't actually kind of match up with reality. So what is reality? Now, you have to forgive me, I looked. I'm sure there's a paper out there, I just couldn't find it. But there was a publication that looked at the breakdown of percent glandularity, and this was done here in the US, where they looked at about 3,000 patients. They took all of their mammograms, and they looked at the percent density of glandularity and thickness and a bunch of other things. So here, let's look at the plot on the left. You can see here as a function of age, younger women, they tended to be here. You have predominantly fatty, scattered fibroglandular, heterogeneously dense, and extremely dense. So the younger women tended to be heterogeneous to extremely dense when it comes to fibroglandular, to glandularity. And then as you get older, you see that the right side of the shift is these dark purple, yellow, they start to shrink, and this blue and light kind of purple lilac color, I guess, starts to increase. So as older we get, it becomes less dense, more scattered fibroglandular, and it trends towards fatty. So we already know this. I mean, we know this by inspection. We've been looking at mammograms now for many decades. And then you look at the overall histogram of compressed breast thicknesses. The values here in black are for a CC, craniocaudal view. The average thickness here, so the peak, the mode in this case is 5 centimeters. And the average is somewhere pretty darn close to 5 centimeters. So it's not actually 4.2, but it's actually closer to 5 centimeters. So this idea of a 50% fibroglandular, 50% fat, and then a question of should we consider or assume that there's a 5 millimeter subcutaneous fat layer underneath the skin? This whole model right here that I'm talking about, that was proposed back in 1979. And so, does it actually exist? Well, I showed you the breakdown of I showed you the trending, so we know that glandularity changes with age. We also know that breast thickness is actually not on average 4.2, at least in the US. Admittedly, I couldn't find any studies for Thailand. But what about glandularity? So in a separate study of 2,831 women, this was US and Canada, so once again, more Western population. They also included, so that's 2,831 mammograms, and they looked at 191 CTs. So I don't know if Thailand has this, but there are dedicated CT scanners of the breast, and we have some of those here in the US. So it's not a CT of the body itself, it's actually a CT of the breast itself, specifically. All right, I'm sorry, I misspoke here. Total of 2,831, 2,640 mammos, just shy of 200 CTs of the breast. So once again, they looked at what was the average glandularity. So if you just look at the histogram here, the mode is going to be here right on 15. But the mean, when you look at it, breaks down, is actually just shy of 20%. It's actually 19.3%. Here you can see the first quartile, 13.7, and the second quartile, the third quartile, the 75th percentile, is the 25.6. So the vast majority of the patients are right here, somewhere between 13 and 25% glandular. So where is the 50-50 breast? If you look over here, 50% glandularity is less than, in this total count, so it's a histogram, there were less than probably 50 patients out of 2,800 patients. So not very common to find a woman that has 50% glandularity. Now, in this study by Yaffe, they looked at the overall volume of glandularity. In one of their calculations, they looked at it that included the skin line, and another one where it did not include the skin line. And that was based on the way they thresholded the images so that they could separate the fat versus glandularity. And as you know, looking at the image, skin is highly attenuating too. So the skin and the glandular material, you know, the ducts, the structure, the ligaments and all that, the vessels, all of that, they all tend to attenuate similarly. So they all appear basically the same. So it was a little bit harder for them to separate, but they did do their best to separate it. There in this publication, they actually measured a mean average compression thickness of almost 6 centimeters. So slightly larger, or I guess less compressed than the last study that we looked at. And so here's the averages. I just simply point out the fact that depending on how they calculated, if they calculated the mean glandular volume when you consider skin, that's how it came up with the 19%. If you take the skin out of the calculation, so it's truly just the glandular material inside the breast, the average is actually 14%. So that 50-50 model, I guess the take-home message here is that 50-50 model is really not that accurate. So when we're calculating dose to mean glandular dose of 50-50, 50% glandular, 50% fat, in most cases, you are way overestimating the actual dose to the patient on the scanner. Because statistically speaking, as we just showed, most of those doses are, most of those breasts are not going to be 50% glandular. Now, we also know that that has a big variation with age. We already showed this, but the point I wanted to show in this Yaffe plot is look at the error bars here. So the vertical here is the volume of breast of the glandularity, and so you can see here there is, you know, the younger you are, the more glandular these women tend to be. So there is a certain population in the younger era that could be your 50-50, but as you definitely trend older, especially as you're getting out towards 70 and 80, this is where that mean is shifted so low of 19%, because, you know, the majority of women getting mammograms are over 40, and they tend to be, and that population that is starting to skew more fatty, or more fat per volume of the breast than the glandular tissue. All right, so just a quick summary of what we've been talking about. Singular dose metric that we use currently for diagnostic reference levels, my apologies, that's typed wrong, DRLs, is the mean glandular dose, or the D sub G. The D sub G, we went through all the different ways to calculate that for full field digital mammography, and I showed the one way we calculate it for the tomosynthesis. And we talked about how the values reported, so the values you are collecting for your DRLs are going to have an inherent error based on which machine it was collected and which method those vendors used. So that error is roughly 18%. And then we talked about the standard breast dose model as we collect with phantoms. So when we calculate the mean glandular dose, we went through how we calculate that. And then we talked about the fact that this whole 50-50 thing doesn't exist. And so if your calculations are assuming 50% glandularity, you are in most cases overestimating the actual dose to the lady being imaged. All right, that's what I got for the first talk.
Thank you so much, Sam. So one thing that I got from your lectures, it seemed like that is a little bit complex for the dose on the mammogram because of the vendor, depends on the machine, depends on the filter,
Yep.
and it's not like a user friendly when we're trying to collect the data for the mammogram, which is going to cause a lot of issue for us.
Yeah, and this is true. So you guys have already done a round of DRLs, and we're talking about that in the next talk. The reality is that's just what you have to deal with. I guess the point of all of this, I hope you take away with, is the fact that the numbers that you will now collect, now that you got all these different hospitals out there with their dose monitoring software, they're collecting that data from their mammogram systems. And it's going to be a mixed bag. It's going to be some GE, some Hologic, some Philips. It's going to be whatever you guys have. And those values are going to be reported. And though there's going to be an inherent error of about plus or minus 18%. And then when you collect all of that data and you send it off to the central location, and then you have all of that data collected, now it's across all of your hospitals, all of the ways you use it. You just have to understand that when you calculate and you report your 75th percentile, your DRL, and you then send that back to all the hospitals, that there is just that inherent measurement error and that inherent error from based on the calculation. So I guess my point is when you guys represent a value, which you guys calculated your DRL of basically 2 milligray, that value, plus or minus 18%, at a standard machine, if it is close to your DRL, could be plus 18 or minus 18% of that value. And that may be not because the image quality is bad. It may not be because you're overdosing the patient. It may simply be because they used the Wu calculation or the dance calculation or the Boone calculation. So ultimately, that's just what we're dealing with. What we need to do is always do our best to try to get under the DRL. But we've said this all along. You look at the image quality, you look at your doses, and then you have to put the two together and ask yourself, do I have room to drop my dose? Because is my image quality okay? Or am I looking at my images right now and I kind of think I couldn't lower my dose anymore? And if you're okay with the image quality, but you don't really want to drop your doses, and you're right at or maybe just a little bit above the DRL, that 18% value should probably make you feel okay. Now, if here's the DRL and you're more than 18% above the DRL, then everything we've talked about, all of this variation, that has nothing to do with the fact that you're overexposing based on the national DRL. In that case, you should do your best to drop it down closer to the DRL.
So are you trying to say that 18% is like a buffer zone for the filter, for the vendor specific, and for the formula, which is like an acceptable area for the overall picture when we have the national dose? And if each hospital want to go back and look on the on that technique, specifically on the vendor, they need to call medical physicists and ask them to do the real measurement and dosing, and also look at the lookup table. But for the overall picture, we use an 18% plus and minus to be a buffer zone.
So there's kind of two answers I would give to that.
Okay.
The simple answer is, if you have the DRL, you do your best to try to get your value closer to that DRL. But you have to look at your image quality. So that's the simple answer. If you don't have a medical physicist and you don't want to think about it, you just look at, okay, if I'm all the way over here, Maybe I reduce my dose a little, look at my image quality, it's okay. Reduce my dose a little, look at my image quality, it's okay. Reduce my dose a little, and I'm starting to not like it. So maybe I back it up a little and I stop there. Now the question is, okay, what does that 18% mean? So yeah, now if you have physicists and you have the ability to go in and do these calculations, you can go in and you can actually look at each of the vendors. So let's say you have 2 or 3 at the hospital or whatever imaging site you have there in the region. And you can look at, it's Sectra, it's or Philips, I should say, GE, it's Siemens, it's Hologic. You have all of these vendors and you can go in and you should do some kind of annual dose calculation. In the US, it's required by law. So we have to do this annually. Every one of our systems, we have to calculate it. And as we talk about in the next talk, all of our dose calculations have to be below a certain value. There's a threshold. And if the system is above that threshold, you cannot use the machine. And so I don't know to what extent Thailand has adopted similar standards. I know the IAEA basically has the same recommendations. So I assume Thailand's probably following the IAEA. And then what you do is you can go in and you look at the values, and that 18% will tell you how you can adjust your outputs. So if you are making your measurements and you are, right at the threshold or maybe a little bit above, you need to dial that down because of that 18% threshold can go both ways. If you're below that value, but you're barely close to it, say this is the threshold and you're just really right below, remember that plus 18 can actually push you a little higher. So you may still ask yourself, can I go a little lower? But once again, everything is always based on looking at the image quality. We've talked about it from the very beginning that just simply turning down the dose is actually not an appropriate thing to do in radiology. The radiologists need to be able to make their diagnosis. And mammography, as we talked about last week, is particularly difficult. We're going to talk about dose optimization next. We're going to talk about all the tools and tricks we have to make the image better, the dose better, based on all the image stuff we talked about last week.
So maybe the questions that we have here, you can answer after the next talk. So the question is about right now we have the AEC system. So how can we reduce the dose level for our protocol? Do you have like a density level set?
Yeah. So the answer is there's a couple of things we can do. Let's talk about that in a minute because I have a whole lecture on this.
Okay, sure. That's good to me. So I think we can go to your next lecture.
Okay. So that's a great question. All right, let me grab my next talk. All right, you should see my screen now.
Yes, I can see it.
All right. Oh, another question popped up. Do you want me to answer that? Let's see.
You can answer. So the next question.
Hong is asking, for stochastic effects, do we use AGD or effective dose? That's a good question, Hong. So the answer is when you look at stochastic effects, that is based on population average doses, and that's effective dose. That said, if you look at, for example, the reports from Hiroshima and Nagasaki, from all of the studies that we've been doing from the atomic weapons, they will give you lookup tables and plots based on effective dose and actual mean glandular dose. So you can actually use both. But most of the time when we talk about quote unquote risk, we usually talk about effective dose, which is in sieverts or millisieverts. So good question. Okay, so let's talk a little bit about optimization. So we talked about how to calculate the dose. That's fine. But what does that mean in the bigger picture? So real quick summary. When we image for mammography, we need to be able to see high spatial resolution and good low contrast noise, really good low contrast noise resolution. And we talked about this last week, how these two things are opposite. To get good spatial resolution, you want a small focal spot. Therefore, it limits how much MA we can use. But to get good contrast to noise resolution, we want to use high MA, which requires a bigger focal spot. So the balance of these two things are really, they're diametrically opposed, and we have to fight this battle this whole time. We're trying to optimize for mammography. And the overlying problem with all this is we use mammography for screening. Therefore, we're taking asymptomatic women and we're asking them to be imaged every year or every 2 years. And then therefore we have to make sure the doses are low. It's one thing to image someone that has a known cancer or known disease, because the benefit is always higher because we're trying to treat the disease. But if you have someone that has no disease, has no known issue, then the risk potentially of exposing someone consistently to a lot of radiation, maybe the risk is too high for the benefit. So we keep the dose low so that in a screening process, the benefit is always higher than the risk. When we talked about imaging, we talked about the various different factors that go into creating an image. And so the values shown here in blue, we talked about for image quality. No surprise, of course, the same factors that affect image quality will also affect patient dose. So we're going to talk about each one of the values shown here in blue. All right, so the dance method to calculate mean glandular dose, remember, we talked about this equation a moment ago. That value S, which deals with the spectrum correction, that has everything to do with the type of filter, excuse me, target, anode that we deal with. So in mammography, the three most common targets are molybdenum, rhodium, and tungsten. And last week we talked about how tungsten has become more common. In fact, basically all new mammography systems, except for one vendor, all use tungsten now. It surprises me that we haven't 100% moved to tungsten. I'm sure at some point, maybe that one vendor will eventually move to tungsten. And that's just simply because we don't do any film anymore. At least in the US, we do not do 99.9 or 99.8% of all mammographies are digital now. And so film we needed to use moly. We needed to use the molybdenum and the rhodium targets for film. We absolutely had to. Tungsten wouldn't have been good. Those film images would have looked pretty horrible. So we take the target and we always add it with a filter. We need a filter in mammography. And the filter does two things. It gets rid of these really low dose, low energy photons, which are nothing but skin dose. We talked about everything less than 15 keV does nothing but increase the dose to the skin or to the surface of the breast. And then all of the values over 20, anywhere in the range of 20 to 25 keV, have the tendency to decrease overall image contrast. So the filter we're going to choose is doing our best to remove these photons and focus on these photons as the primary photons to do imaging. Now, we talked just very briefly, I'll review, we talked about the combinations, how they're very important. So when you look at the dashed line here, this is a moly filter, and this moly filter has a K edge right here of 21 is like 20.5, I can't remember, it's 21 keV. And the reason everything underneath this dashed line will be absorbed. It will be removed. So when you use a moly filter with a moly target, you don't get a lot of high Ke energy photons, and you don't get a lot of these really low ones. That's great. You can see how the spectrum is nice and shaped for that, the perfect or the sweet spot for image contrast. And the same is true if you use a row filter. Now the row filter has a little bit higher atomic number, so it has a little bit higher shift in the spectrum. So the row will actually remove a hair more of these low energies, but it will keep some of these higher energies, this orange right here. And that's meant because back in the day, we used Molly row targets, filter combinations for the thicker, denser breasts where we needed more photons to penetrate. But like I said, we basically have moved towards tungsten. And the problem with tungsten is you have these L X-rays. So not K edge, but these L edge rays. And these values are all down here in the 10 keV range, which is nothing but skin dose. So whatever filter we use, they have to get rid of these values right here. So common to this are tungsten and rhodium, which you can see this dashed line is rhodium. So it gets rid of this value here, and it gets rid of some of these high values. But other common ones are silver and aluminum. But they're mostly focused around that 20 keV. They're really good at reducing skin dose, and they're pretty good at getting rid of the high keVs too. The reason we've shifted more towards higher atomic number targets, tungsten, and higher atomic numbers for your filters is because film has got a larger dynamic range. It doesn't have that S value, you know, that H&D curve that we've always come to know in film. It's linear, so we can actually change the contrast very easily digitally. But also, when we shifted towards breast tomosynthesis, there is a lot of inherent contrast in breast tomosynthesis because we take the plane of the breast that we reconstruct and we blur everything above and below. And so everything in that plane is very sharp and crisp. And so we can just kind of make those cuts, you know, like a slice or a loaf of bread. And we look at each slice of that bread or slice of that breast, and we get really good contrast. And so because of that, we can actually take more high energy photons, and it really doesn't affect negatively our image, the contrast in that image. So you're going to probably ask the question, as was asked, you know, how do we optimize the machines, or how do we optimize dose? Well, the first thing we deal with is the target filter combinations. So in a study by this group down here, they looked at tungsten rhodium, Molly, and Molly row. And they asked the question, which target combination would produce the highest patient dose or higher patient dose? And when they did their study, they found that the Molly target produced the highest dose. Molly rhodium was 10% higher than Molly and higher than the tungsten rhodium. But what ended up happening is, because we know when we typically use the rhodium filter for thicker breasts, when they actually normalize the data by patient thickness, so now it's dose per patient breast thickness, then the Molly gives you 0.46 milligram per centimeter, Molly row is 0.33, and then the tungsten rhodium is 0.28. So the take-home message here is, as your as your X-ray spectrum gets higher, or you know, you get a higher half value layer, the dose reduction comes down. So Molly was the least penetrating. It had the lowest half value layer, which makes sense. It's going to have the biggest dose per breast as a function of thickness. And this right here is why we get really good dose reduction in digital mammography these days, because we typically use tungsten rhodium, and it's basically almost half of the Molly. Now, let's take into account image quality. So it's just like I said, we've been saying how you can reduce the dose all you want, but how does dose change as a function of image quality? In a different publication, they looked at their figure of merit, their FOM, was CNR squared divided by mean glandular dose. Now, these plots might be a little hard to see on your screen. You can always take the PDFs at home and zoom them up if you want to, that I sent out. But basically what you're looking at here is the dashed line on the very top. that right there is tungsten rhodium. And then the one right below it, the thinner, the more tightly or closer spaced dashed lines, that right there is moly rhodium. And then down here is moly moly, and then there's the moly moly is this solid line right here, and this dashed line right here, that's tungsten silver. So the point here is for basically less than up to 4 centimeter thick breasts, the value, the use of tungsten rhodium was better, yes, in dose and image quality, but not that much better than moly rhodium. So you could technically still use a moly rhodium or a moly moly, well, not a moly moly, but a moly rhodium for 4 centimeters and less. But the minute you go from 4 centimeters on up, the tungsten rhodium shown here is hands down, produces better image quality as a per dose than the next competitor, which is moly rhodium down here. And then the interesting thing here is as the KV gets higher, which probably means thicker breasts, the tungsten silver right here, tungsten silver, it passes the moly rhodium, and it actually even passes the tungsten rhodium all the way out here to really high KVs, thick patient breasts. And then 6 centimeters out here, same thing, moly rhodium, and then the moly silver. Excuse me, tungsten rhodium, tungsten silver. So the point here is tungsten rhodium by far gives you good image quality as a function of dose. And so that is why most vendors are moving this way. Now, if you have a system and it gives you the option of all of these filters, then setting up protocols based on tungsten rhodium will give you good dose optimization for image quality. Now, not every vendor gives you that option. As I've mentioned, there's one out there that doesn't. So it's just not an option. Moly rhodium's the best you can do. I'd use it. If you have the option for tungsten rhodium and tungsten silver, then when you're setting up your protocols for your thicker patients, the thicker breast protocols, the thicker compressed breasts, you may consider, once you get out beyond 6 centimeters, using tungsten silver. Now let's look at that as a function of view. We already kind of know this to be true, just intuitively if we think about it. So for a tungsten rhodium target filter combination, the MLO is about 8.5% higher than a CC. And then for the moly moly and the moly rho, the MLO is about 9.1% higher than a CC. Well, we know as we're imaging medial laterally through the medial lateral oblique through the breast, we're imaging towards the axilla. We're going to image more of the pectoralis muscle. So there's just more attenuating material in the image, and the density and the thickness will be slightly different as you're coming in at a different angle. So because you're just needing to image more tissue and more and thicker or denser tissue, it just makes sense that the MLO is going to be a little higher than your CC. And so we'll talk about this, but this is why and I know you guys did it, but this is why you guys want to set up your your diagnostic reference levels for CCs and MLOs, because they are different doses. You expect them to be. We, of course, talked about compression paddle, how it's great for reducing the amount of scatter in the image. You compress a breast, you're reducing the scatter by more than 50% typically, and that improves image quality. But it also reduces the amount of dose, because if you have thinner breasts, we need less photons to penetrate the breast itself. And then just to comment here, all of our dose metrics that we use to calculate breast dose, 2ABD and mean glandular dose, or D sub G, they all took into account breast thickness. So compression of the breast is a very important metric. And we talk quite a bit about this. There's different ways to do this. You can either do it based on your force calculation, so making sure your force is fully calibrated, or the new one, which is pressure, which is force times the area of the breast being compressed. We very little talked about grids for image quality, but they're very important because they reduce, of course, scatter. You can see here the amount of scatter as a function of different thicknesses of breasts. Thin breasts really don't produce a lot of scatter. That makes sense, right? Thick breasts, 8 centimeters, produce a lot of scatter. That makes sense, right? But what does that do using a grid to the dose? Well, when we put the grid in, it has a Bucky factor. We talked about this when we talked about DR and CR. And that Bucky factor for mammography is about 50 to 300% increase in MAS. So you slide the grid in, and if you're imaging anything from a relatively thin breast to a thicker breast, you will see the dose or the MAS go up by at least twice, all the way up to 50%. It'll be goes up 50% all the way up to potentially 300%. That's just part of the process because the grid itself will absorb a lot of the photons, so you just need more photons to get to the detector. And this is why we do not use the grid for magnification mammo. We talked about that. And we typically don't use grids for digital breast tomosynthesis, with the caveat that there are some vendors that have very specific grids for digital breast tomosynthesis. The grid itself has to be focused so that when you're sweeping at different angles, that the grid will accept all that. Because if you have the wrong grid in there, it'll cut off, it'll absorb a lot of those photons, and you'll actually get it'll be bad for the image quality. So there are some systems out there that do what are called step and shoot, and because the system will move, acquire an image, move, acquire an image, move, acquire an image, it can align the grid very specifically to every angle. But there's a lot of systems also that have just continuous sweep, constant motion, constant imaging. And because of that, they typically don't use grids. So when possible, if the image comes across and it looks just a little grainy or it doesn't look as good as you want it, use imaging, the digital post-processing tools, to try to enhance the contrast, enhance the image quality before you retake the image. All right, we talked about air gaps there. This is a very specific way to reduce the dose when you do a magnification mammogram image. And that's just simply because it reduces the amount of scatter collected on the detector, which is true. And because of that, we can offset the dose. The dose to the breast gets higher as we get closer to the source, but when we take the grid out, we reduce the Bucky factor. And so that reduces it, and it basically keeps it constant. So breast up here versus breast down here with a grid, they're basically the same. So let's talk just in brief about the various different detectors that we use in mammography. And this is all digital. We're talking digital. Film, that's a different creature. It's a different beast. So digital systems, the most common is the indirect panel. That is where you have the cesium iodide, the photon comes in, it interacts with cesium iodide, it produces a light cascade, so you get all these light photons. They're collected now on the photodiode, and that is then how we collect the signal and process it. These systems typically have a really good spatial resolution. They have a high 100 micron pixel pitch, and cesium iodide amplifies. So for every one X-ray photon comes in, you get hundreds, maybe thousands of light photons. And so because of that, indirect TFT panels are the lowest glandular dose systems on the market. Because for every one X-ray, you get a factor of 10 to 1,000 or even sometimes 10,000 signal out. So it's a great amplification. Whereas the direct, now we're using amorphous selenium, and this system where the photon comes in, it interacts with the selenium, and then you create and you liberate an electron. That electron will migrate to one side, and the lack of electrons will accumulate on another side, and that allows for current to flow. These systems have the absolute best spatial resolution because we talked about this in DR imaging, but we place a electronic bias across the system, so it helps steer these electrons. When the photon comes in here and liberates this electron, that electron will not spread. That electron will not travel. because there's an electrical bias here, that electron will go straight to the bias, and then the lack of electrons will be on the other side. So great spatial resolution, but it's going to have, because you don't have a cascading effect like you do up here, you don't have that amplification of signal. Therefore, the dose tends to be a little bit higher. You just need more photons in this kind of situation. The system that the digital system that produces the highest mean glandular dose is the CR system. CR plates are on their way out. Here in the US, the vendors of the CR vendors, they don't create CR plates anymore. So all of our CR systems are going away. I don't know how it is in Thailand, but I assume it will be, if it's not happening now, it will be sometime in the near future where those systems will go away. And they're less efficient than the digital systems we just talked about in the last slide. They're still great. If you have an old film-based mammogram unit, well, you can retrofit that to just simply place a CR plate in there instead of a film cassette. And then you can go obviously and use the CR plate and read that out. Then there is a system out there, the sector that does slot scanning, and that's where the detector and the tube will slide across the body. Well, not the body, across the breast. So if you're doing a CC, the breast is compressed in a CC, it's going to slide across like this. Obviously, it'll do the same thing in MLO mode. The system produces really good scatter rejection, so because it has a very narrow aperture, narrow collimation. Therefore, it doesn't necessarily need as much radiation. But the system typically is on for a long time, 5 seconds or so, because it just takes a finite amount of time to scan the entire breast. Bigger, thicker breasts, the broader the breast as it's compressed requires more scan time. So therefore, there tends to be a little bit more motion error in this. This isn't not as common, these slot scanning ones. Most common by far is this indirect system, and that system gives you the best lowest glandular dose. So take-home message here is, if you have the option when your hospital is buying new systems, new mammogram units, and they come to you and they ask you as the managing technologist, the lead radiologist or physicist, you would say, hey, when you look at the options out there, I would get the indirect system. All right, we talked about AEC, and this was one of those questions that came up. So when we set the AEC up, you're going to need to set or establish a good operating KV. And then the system, of course, once you have that KV, will produce the MAS. And so when you look at, so this is a publication from Bigala and their colleagues. What they did is they looked at a couple of different target and filter combinations, and then they looked at protocols based on patient thicknesses and setting up different KVs. And they measured the radiation doses. And so without too much surprise, the higher the KV, the higher the mean glandular dose. We know that. That's true for X-ray, that's true for fluoro, that's true for CT, that's true for everything. Higher the KV, higher the dose. KV changes as a factor of 2. And then 28. So here you can see 32 kV, 28 kV, the 27 kV, which is not much different than 28. So why they had those two separate protocols was, it is what it is. You can see just by this data right here, you could probably combine those two protocols. And then the blue down here, which is going to be your smallest or your lowest kV. So you can see here, getting the right kV as a function of breast dose is going to help your system pick the right MA to give you a good optimal breast dose. And then when you look at so you're going to have that for your tungsten and your whatever combination of rhodium or maybe even silver if you have it. And then if you have systems that still use moly-moly or moly-rho, here now is a comparison down here. They, of course, use 26, 27, 32. In this case, remember how I said there's really very little difference here. I know the digital systems can be more finite. You can go 25, 26, 27, 28 kV. You can have all these different protocols based on all these very small steps. But when you look at this breast, you look at the data compared to the actual breast thickness, and you see that there was really no difference. So in this case, in this case, they combined those protocols. So 3 to 6 centimeters, they only used 1 kV, which is shown here, the red. And then 32 kV, of course, for thicker breasts. And then there's the 26, very few, but they're just down here. Small, thin breasts, not a lot of MA. And overall, you can see comparison-wise, the steepness of this graph of these green dots, 32, versus these green dots, 32. So it's the same KV. The difference between this is tungsten rhodium. This is moly or moly rho. And you can see that using these moly rho, remember, it was about 0.2, 0.3 milligray per centimeter difference. Higher dose for these protocols than these protocols up here. So let's talk dose reduction in general. What are the recommendations? The IAEA recommends that all mean glandular doses are less than 3 milligray per view. In the US, it's actually mandated by law. So I just assume that Thailand probably follows the IAEA recommendations. So what does that mean for our standard imaging? Contact mammo with grid in place, assuming a 4.2 centimeter thick breast with a 50-50 breast composition. That is the standard breast model. And if you have that breast model, that should be less than 3 milligray. In the US, we also specify for magnification mode. So breast is closer, it's in mag mode. The mean glandular dose needs to be less than 1 milligray. And once again, this is without a grid. And then when you look at the effective dose, kind of like Hong was asking about risk, in US, we are basically 0.3, 0.4 millisievert per view. And that is approximately equal to 4 chest x-rays, chest radiographs, PA chest radiographs. In Europe, their mean value is 0.27 or basically 0.3 millisieverts with a range of 0.02, which is incredibly low. That's very low, to 0.6, which, it is about half, double the mean, which makes sense. You got some bigger, thicker breasts out there, less compressed breasts. So that's just a couple of numbers to give you just as a highlight, an idea of where the effective doses lie. But once again, we're mostly focused on diagnostic. For DRLs, we're mostly focused on mean glandular dose. So dose reduction for full field digital mammography, we have seen over the last couple of decades as we've transitioned here in the US to digital from film, we've seen an immediate reduction in dose by about 20%. And that's just simply going from one machine to the next, just going from digital from film. As I mentioned, I quoted you wrong. 99.5% of all the units in the US are digital. So one way that you will reduce your overall population dose in Thailand is by completely modernizing mammography. I don't know what percentage you still have of film mammograms in Thailand, but simply getting towards digital is a way to reduce your overall female patient population, the breast population dose, by 20% on average. Additional dose reductions are made possible by improving your beam quality. So using a tungsten target, more efficient detectors using an indirect system, and larger detector sizes. And that is simply because if you have a relatively small field of view and you have a large breast, you're going to have to make 2 images where you're basically imaging the breast twice just to get the whole amount of tissue in the image. The larger the field of view, obviously you'll be able to acquire everything in one image. And that is especially true for the MLO because you're trying to get the medial side of the breast, which is harder to see in a CC, but you got the medial side all the way up to the axilla side. And so that's just a lot of territory to cover that you need to make sure you have a good size field of view for that. So the single view, as we measure this here in the US, we're on average about 1.4 milligray. And that's down from about 1.7 milligray from our film days. 2-view full field digital mammograph. So per breast, so you got a CC and MLO, that's less than 3 milligray. That's doing pretty good because our standard, as you may recall, and what the IAEA recommends is less than 3 milligrays per view. So that would be 6 per breast, CC, MLO, so 3 and 3. What does digital breast tomosynthesis mean to the dose landscape? Well, we've already talked about how digital breast tomosynthesis has a lot of positive qualities when it comes to image quality, to diagnose, the ability to diagnose, the ability to detect disease, less false positives. And so we have seen here in the US a significant shift towards digital breast tomosynthesis. And the mean glandular dose for a 1-view tomosynthesis, so CC, DBT, is comparable to the full field digital mammography. So it's great. Here is just a spectrum or a plot of doses using the 2ABD methodology as a function of breast, or in this case, phantom thicknesses. Here's that roughly 4.2, 4.5 standard breast model. Here you can see the digital, so the full field digital mammography is in orange. And then the green is DBT, so tomosynthesis. So tomosynthesis is still just a hair higher in dose than standard full field digital mammography, but it's not that much higher. Statistically speaking, in some cases, there is no difference. In other cases, there is, but for the most part, it isn't. So we're talking about 1.2 milligrays in this publication for a full field digital mammography, 1.5 for the standard model for DBT. That combined is less than 3 milligrays. And so that is why pretty standard here in the US now is women will come in, they'll get craniocaudal, MLO, full field digital mammography in contact mode, and then they'll do a breast sweep. They'll do a tomo sweep. It is worth pointing out that there are some publications out there that show breast tomosynthesis is actually is less dose than full field digital mammography, which is obviously a little different than what I've shown here from this publication. But the point here is it's basically comparable, maybe a little less, maybe just a little more. And the whole concept here is this whole 2D plus 3D is now less than 3 milligray. So what does that mean? So let's look at Thai DRL. So you guys have done great. A couple of years ago, you went out, you've collected a lot of data. You obviously got your max, your mean values here. So you got a good range, upwards of 5-6 milligray. That's actually very respectable. Your mean value is 1.7. That's wonderful. Like I mentioned, that's comparable to kind of what we're seeing here in the US. Your DRL, basically 2. That's great. How does that compare? So I went out, looked at a publication or Suleiman, different publication than the ones I've been showing you from Suleiman. This guy and their team, oh man, they looked at, I can't remember now how many studies, and they looked at studies from all over the world. And they basically compiled all the different DRLs around the world as a way to just kind of do a quick comparison. So neighboring countries in your neck of the woods, in your area, Australia, their DRL, 75th percentile right here. For DR, so digital radiography, these you can probably, your indirect systems, that's about 1.1 mean glandular dose. Their CR, of course, we know CR is higher. In this case, it's 1.36, so the overall average is 1.3. Taiwan is 1.75. Down here, Malaysia, 1.44. And then just quick comparison for us here in the US, as I mentioned, we are just shy of 2, 1.9. Our total is 2 when you compare everything. Here's a couple more folks from your neck of the woods, Japan, 1.9. And S just stands for standard. So your standard medial, lateral, oblique. So in this case, Japan also, in this publication, they didn't specify. So I don't know if that's CC or MLO, probably CC. In this case, Japan, in this publication, they look at SMLO. So that's 2. So that's good. Here is Europe, 1.6. And overall North America, so that's going to be Canada, that's going to be everything kind of lumped in. So that's why the number is just a little lower than the US one on the previous slide. Asia Pacific, 1.1. And that's going to have a lot to do with Australia. Remember, Australia on this last slide is super low, 1.1. So Australia kind of pulls the Asia Pacific down a little bit. But you got your islands and whatnot, New Zealand and whatnot. So here it is, just kind of a take-home message. Here you are, Thailand. I just added you to this group. You're blue. You're basically 2.1 maybe, 2.1 maybe here, but basically 2. You guys are just right on par. There's a few out there that are a little lower. We know Australia. They don't use a lot of radiation, or they just have really, or they just compress their poor women a lot. And then Taiwan's a little lower, which is comparable to you guys, just neighbor-wise and population. And obviously here, US, we're just kind of we agree with you guys. And then some of the European Eastern Bloc countries are a little higher. So you guys are just right on. A little bit, some are a little higher, some are a little lower. As you guys move towards the future, here's just some questions that I asked. Questions that you can either answer, or we can either talk about in the conversation in a moment, or you can think about as you go forward with the next round of DRLs and mammography. So you guys have 865 mammo units as of the time of your collection. So my question is, what percentage of those are film? If there is a certain percentage that are film and persisting in film, then you should probably include a DRL for film. My guess is you probably are mostly modern, mostly digital. So that's probably why you've only included digital. At least I assume this is probably an average of digital and film. I mean, excuse me, the digital, this is an average of the median value, and it's predominantly probably digital is what I'm trying to say. But if there is a certain percentage that's film, I would separate the two, because I bet you'll find your digital is much lower than your film. And then this question is DBT. So you saw back here, all of this is CC-MLO. Nowhere in the country, excuse me, in the world are people really collecting good digital breast tomosynthesis data for DRLs. But as I mentioned, here in the US, that we have trended almost completely towards DBT. In almost most instances for screening mammography, we do FFDM and DBT. So when we go forward with our next round of DRLs, we will be including, we absolutely need to start to include DBT. So I strongly suggest that to you guys also. You guys can collect a fulfilled digital mammography, CC, MLOs, and the right and left breast, and do the same for DBTs. So you'd actually just have 2 columns there. And then this is more for statistics. So these are the values you publish for your diagnostic reference levels. That's awesome. That's great. But then when you report back to the vendors, we've talked quite a bit about the variations in breast thickness and the machines and all of that, that plus or minus 18%, there is that inherent variation. And so when you give information back to the various different hospitals, the more granular you can get, if you have the statistics to do this, that the more they're able to focus in on optimization, especially for centers that may not have a medical physicist working for them or in the region helping out. So if you can include what the compressed breast thicknesses are used for this statistic at a minimum, let's say the average was 5, like we've seen in some of the other publications, that's fine. At least they know that when they look at their data, they find their average for 5 centimeter thick breast, and then they try to compare their dose to the DRL from there, their median value. If you have a good spectrum, you have a good histogram, you have good statistics, then you maybe reproduce it. You give plot as a function of maybe 2, 4, 6, or 2, 3, 4, 5. You give as a function of different breast thicknesses. Include the KV and the MAS that produce that. So when you collect that data, as it's now becoming more digital for you guys, because you're getting software spread across the country, you will have the KV and you'll hopefully have the MAS and you'll have all of that. and you can collect that from the metadata. If they send in an image with the dose reporting, then you have everything. You could even technically calculate using, the dance method or the Boone method, etc. Or excuse me, the 2ABD method. And so you could report back to them these values. So say this RCC, this right craniocaudal, they gave a 2.05. That may have been for like a 25 kV at, I don't know, whatever MAS. And so it's just helpful for them to really kind of focus in on how the other hospitals can set up their quality control. So just in summary, full field digital mammography has made it possible to reduce doses in mammography by 20-30%, just straight up out the door. You buy a new system that's full field digital mammography compared to film, you immediately get about a 20-30% reduction. Additionally, if you move away from Molly and Molly Row towards a tungsten-based target, you get more dose reduction. Remember, tungsten Row was almost half, it was about 40% lower than Molly, and then a little less than Molly Row. Compression is still key to reducing patient dose. Less thickness equals less radiation, less thickness equals better image quality. So we talked a lot about compression last week, about that being the key for image quality. It's still very much part of the picture when it comes to imaging for, radiation dose. It's just that there's other things like setting up the right target, filter combination, and KV that we talked about. I also mentioned how you get all of these great dose reductions as a function of going from film to digital. But overall, the dose to our population is kind of held constant through this time. And that's because we've gone from digital, full field digital FFDM plus DBT, so 2D plus 3D. No doubt there is the potential to still see doses go down a little bit as we get better and better with our 3D imaging and maybe 2D imaging. So, but why do we do this with the DBTs? I mean, technically, if you strip that out and only do 2D imaging, you get half the dose than we were a decade or two ago. But we know, as I've mentioned, DBT increases the number of detected cancers. It reduces the false positive rate, especially for younger women that tends to have more dense breasts, and so, or more glandularity. That's what I'm trying to say. And so in those populations, DBT is a no-brainer, straight up. But maybe as they get older, it's more fatty, less, better inherent contrast with glandularity. Maybe the use of DBT goes down, and you should look at that at your population as you kind of review this in the usage of DBT. Future DRLs should include DBT data, as I just talked about. I mentioned that there is a potential that I think in the future DRLs will include 2ABD instead of just mean glandular dose. So that's something you should consider as you start collecting this data for the next round. You're obviously going to have your mean glandular dose, and that's just because that's what pretty much everyone's doing internationally. But as we showed, mean glandular dose and 2ABD calculations are fairly comparable. The actual error rate for 2ABD was just a little lower, just a little more precise, and you can actually collect all the information you need to calculate 2ABD all from the image itself. Less lookup tables, less variability in that regard, and you don't have to take into account glandularity. So if I was trying to prophesize and and try to pull out my crystal ball, I would assume that 2ABD is going to be in the future. So you should consider that, how you would start to collect that data, if you could calculate that. Or, here in the US, we have a model where we send in our dose data, but we also send in an image with that. So as you start to build up your capacity nationally, you may eventually move from just collecting dose data, but you also collect dose data plus an image. And as you get that one image, you can do a lot of analysis with it. And you can, of course, do your 2ABD calculations. All right.
Thank you so much, Sam. Excellent, as always. So there is a couple questions that come to my mind. So last on the couple last slides, you mentioned about the Thai DRL that when we have those data collections, so normally we should get the KV and MA, but for the thickness, can we send that send that information, or it should be just like the in-house information for the local people to do some record on those things and compare after?
Yeah, and so this comes down to, you know, I don't quite know, you know, how Dr. Panrutai and her team did this a couple of years ago, but most likely this was part manual, and you were maybe what, and this is true also here in the U.S. This is true in other parts of the world where they use the phantom. They collect the phantom. It's a 4.2 centimeter, 50-50. And they image it and they send that data in, and that is what they use for the DRL. And so it's basically for a standard thickness. But as you guys are shifting towards all dose collecting software, now every woman that comes in gets imaged. That stuff is reported and collected in the system, and the mean glandular dose is reported there. And then that value, those data will then go off and be processed at a higher level. The data that goes from your radiometric system, that goes from your dose collecting software, it may not necessarily have kVMA breast thickness. But if you have the ability to maybe collect an image, you know, so you send one image of that patient's information along with the dose up, then now you have all of this information you see on the screen, because it's all in the DICOM header. You know the compression thickness, you know the breast thickness, you know KV, you know MA, you know all of that. It's all there. And so, at that point, you could then calculate the mean glandular dose or the 2-ABD, and then you could report the doses for DRLs there. So if you use the dose software system, you probably won't be able to do a lot of this higher level stuff. You'll still be able to get your DRLs, and you could maybe still do like a questionnaire where the hospital will say, this is our average dose, this is our average thickness, this is, you know, whatever. These are our technique factors. And then that data can be brought together. You can look at that. You can compare that to all the dose data that comes in from their software, and then you can calculate the DRL from there. But in the future, if you have the ability to collect simply just images, so, you know, the image goes off and you just collect a certain percentage of those and they go off for calculation, then yeah, you can really do some high level statistics.
Which means like we need to communicate with the vendor in case that we need the images to send in for the whole system, right? Because like, the reason to send the images is because we need the DICOM data about the thickness and kVMA, right? And also maybe like when we go back to review, we can say this is a good image quality that we like.
Yeah.
So this is like the basic property or function that the dose software give it to us. So we need to communicate.
Yeah. So Radiometrics, which I know you guys have invested, the IAEA is working with you to get Radiometrics. Radiometrics has the ability to collect KV, mean MA. I want to say it can do breast thickness. I'm almost certain it can. So if you set it up so that the system, so your Mammo unit, sends that data as a structured dose report to the Radiometrics there at that hospital, and that hospital collects that data, mean glandular dose, KV, MA, all of that stuff, then all of that data can go up to you at the national level and be processed. But you have to make sure at the local level, the Radiometrics will collect that. And it's very specifically, that depends on the system. So the GE, the Siemens, the Hologic system, making sure it will push that data to the Radiometrics. So there's a lot of steps going on here as you're trying to make sure the right data gets sent and collected. I'm not saying you necessarily have to send the image quality. That's pretty high level. That's, you know, maybe the third version of your national DRLs in Thailand, because it's going to take a whole different server, a whole different database to collect that data and process it. Different than Radiometrics, completely different. But if you can get the radiometrics streamlined to collect this data, then I mean, you're golden. You'll do good.
Okay, that sounds good. And the second question that I have for you, you mentioned a lot about the tungsten filter. So you mentioned a lot about like a tungsten and rhodium filter. So this is like the filter for the future, right? That gonna give like a better image quality and also reduce radiation dose. And most of the vendor going to move towards that filter.
Yeah. So I mean, you call it the combination of the future, but I would argue it's actually here now. Most modern mammo units. So if you go buy one right now, almost all units will sell a tungsten target. And so then it'll come with a rhodium, a silver, it might even come with an aluminum filter. And then you would then set up your protocols based on whatever you're doing. You'll use your aluminum filter almost exclusively probably for DBT, for your tomosynthesis. But the rhodium and the silver, depending on the breast thickness, is probably what you would use for your filter. As I mentioned, there is one vendor out there that still does Molly and Molly Row. And I'm not saying it's a bad vendor, and I'm not saying their image quality is bad. I'm just saying that still using Molly and Molly Row does have a dose penalty. It just, I'm not even saying that. I'm just reporting what I read in the literature.
You didn't mention the vendor, and I don't know which vendor that have that things, but at least I know when people ask me, or at least I have like some background of the knowledge that if I want to recommend someone to buy the mammo unit, I should look for the one that has like a tungsten. It can be like a tungsten rhodium, tungsten silver, or.
I would say based on the scientific literature, as I've looked at the landscape, that most people are reporting that the tungsten rhodium combination gives really good image quality for a good dose. Like I said, I'm not saying that the Molly is bad or the Molly rhodium, but I'm just saying that from what the scientific literature is saying is that it's trending that way. So yeah, I mean, if you asked me right now as a medical physicist, if my radiologist came to me and it says, hey, we're going to buy 2 or 3 new mammo units, what would you suggest? Right now, I would say tungsten rhodium. I'd make sure it's an indirect detector. Obviously, make sure you get a good size field of view. And there's a bunch of other factors that you'd want to do. But by way of dose, those two, the indirect and the tungsten rhodium, they right there have really good dose reduction properties.
Yeah. It's good because sometimes we just know that we like the image from this vendor. And sometimes we don't really know why we like the images, why the image quality from this vendor is better than other vendor. So that's why our idea just fixed to, this vendor is better than other vendors. This helps us to understand because of the filter that they have that made the better image quality. That's why you like it.
Yeah. Yep. And like I said, it's just, it does have a lot to do with preference, because there are going to be some radiologists that have grown up with Molly and Molly Row. And that's just what they want. And so it is what it is. And if you change that look too much, they'll think it looks horrible, even if the dose is better. So it has a lot to do with, there's more than just radiation dose. There always is more when you consider something to purchase.
That's true. Yeah. So the next question from Hong is the DRL from mammogram standard 4 views. Show as an average for 4 views, average granular dose per exam. So the number that you see is like a per view, right? We like for the whole exam that we need to combine everything together.
Make sure if I understand. The DRL for mammo standard 4 view is shown as an average of the 4 views. Yes, per examination. Yeah. So yeah, it's not the sum. It's not 4 views, because that would be 2, 4, 6, 8. That'd be 8 milligray. And so here on this screen right here, you see the 4 views. Well, you see CC, MLO, right, left. And so the value that you see there is the median value per view. So so Hong in her country, you in Thailand, you're going to collect that data for left CC, left MLO, right CC, right MLO, and you will do the statistics on those 4 specifically, and that's what you have here. And then, as I suggested, I would also, if you do DBT, Or if you're starting to do, I'd still start collecting it. Eventually I would add a second column right there. And that would be, it'd be, RCC DBT. And you would have those values right here. And that's just because and you'll find that they're basically the same. They'll be a little higher, probably just a little, maybe a little lower, depends on what vendor you have. But my guess is they'll be a little higher. But at least you'll know going forward just kind of where they are in the ballpark.
Just for clarification, so that means that a patient has a set 2 per RCC, 2 per LCC, 2 per RMLO, and 2 per LMLO. So which like for 2 breast exam, they get maybe like a 16.
So yeah, so 2, 4 for full field digital mammography, 6, 8 for full field digital mammography, and then if you do 1 tomo sweep for the left, 9, 10, 1 sweep for maybe the right, 11, 12. So that's probably standard right there. Sometimes you might do a sweep on the MLO, but that's typical, at least here in the US, that's typical. You'll get 2 shots plus the sweep. Now we did talk about last week how you can do a sweep, and then from the sweep, you can create a synthetic 2D view. Some doctors don't like that synthetic look. So that is why standard right now in the US, they still do the full field digital mammography. They acquire the CC, they acquire the MLO, and then they acquire the DBT. And that is where the doses are, so 2, 4, 6, 8, maybe for the breast on one side, 2, 4, 6 for this side, 2, 4, 6 for this side.
Okay, that makes sense. And then the next question is about, we can follow with Hong's question. So the average of the 4 views refer to each patient.
In this case, obviously what you see here, this table, that's a population. So that's many hundred. And I can't remember, come on, there we go. In Thailand, you guys had 865 mammo units, but I think you only surveyed maybe 20 or 200, 300. You're only surveyed, I think, somewhere around the 20, 30%, which is fine. Because this was your first go. You probably didn't have access to all of them. In that case, this is a population base. This value is on average a 2 milligray for any woman that would walk in the door, because it's just an average of the population. If you get enough statistics, if you survey 865 machines and you get the data from 865 machines for a year, you're going to have a lot of data. But then you would also have a lot of different women ages and different women breast thicknesses. And so then you could, if you wanted to, start making more complex DRLs. But a DRL is meant to just be a snapshot. So I want to just be careful. You don't want to get too crazy where you have a DRL for every teeny little option out there. This value right here, 2 milligray, is great for you walk into any hospital, any imaging clinic, and you say, irrespective of the woman, be it a 35-year-old high risk or a 70-year-old woman that's on her, she's been getting mammograms for 20 plus years. What we're saying here is any one of those women on average should get 2 milligray per view. And if you're doing that, that's great. Some of these women with maybe bigger breasts, the compression is not as much. So let's say it's an 8 centimeter instead of a 4 centimeter. It's going to be higher than that. So then the person would have to say, is there a reason that I'm getting 4 milligray for the CC? And they look at it and say, oh, it's an 6, 8, 10 centimeter breast thick breast. And in that case, they would have to say, yes, it's higher for a reason. And that's why I recommend in the statistics, at minimum, you should say what the average breast thickness is for this value. Probably 5 centimeters. It's just my guess. And then, as Hong is mentioning, then they have a way to say, oh, this is a 3 centimeter breast and it's lower, so we're good because it's smaller. This is a bigger breast and it's higher, but it's okay. On average, percentage wise, it's okay. But then if you do get enough statistics in the future, you could publish your DRL, and maybe then you could publish the results of multiple different ages, not ages, thicknesses is probably the best way to do it. And then you would have median values for a couple of maybe 4 or 5 breast thicknesses. And then everyone can just quickly look at that and go, okay, here's my hospital average. So here's my distribution. And maybe that hospital is skewed towards thicker breasts. I don't know why. Maybe they're all 6 centimeters instead of 5 centimeter thick compressed breasts. So then they could check their value and make their value align with that. So there's different ways to approach it. The simplest and most straightforward and best place to start is doing it like this. You get one value for the entire population and start from there.
Okay. So 2 follow-up questions from home again. So the survey is for each view of the entire data collected for the population, correct?
I see the survey is for each view for the entire data collected for the population. Survey is for each view, yes. For the entire data collected, yes. So basically you just get all the left CCs. It doesn't matter what thickness, doesn't matter what age, doesn't matter which hospital, it doesn't matter which machine. You just get all the RCCs and you get your median. And then, well, you get everything, your mean, max, median, your 75th percentile, and that's your DRL. And yes, you do that for every view.
Yes, okay. Yep. So
and then, I see. Yeah, she talks about thickness, and so I mean that's step 2. That's maybe step 3. That's kind of in the future, because once you've established what your national DRL is, whatever it is, like I assume, I think this tape would probably be 5 centimeters. Going forward, you get more and more data. Now you can start to figure out kind of where a 3 centimeter or a 8 centimeter breast would fit on the spectrum.
So it's like a national DRL for breast on each view.
Yeah, best place to start. Just like you got what you guys did was is perfect for the first go around. And so this next go around, now that you're getting more data and it's being automated, you're going to be collecting just averages from the actual women being imaged. And that's different. Now, if you're doing this, like I said, with a phantom, because that's all you can do, because you don't have the software in your hospital, in your country, and all you have is the phantom, and you're going around collecting that data, that's okay. But that is based on that phantom, which is probably 4.2 centimeters, 50-50 breast. And so you just have to understand that if you get a value that's, I don't know, 2, it's going to be for a very, very small percentage of your population. So you may see numbers coming from your hospitals all over the country that are just very different. But that's okay, because that value is for a specific phantom. When you have the ability to collect all the data from machines, now it's patient specific, and then you'll see the big distribution of data.
Yeah. So the next question is about, can you explain more about the 2ABD concept and formula?
Sure. I mean, one of the best things you can do is, actually, I'm going to pop out of that screen. All right, you can still see my screen, right?
Yes.
All right, I'm just going to come over here. So in this method, which is the dance method, or, the dance sorry. There we go. These values of air kerma the amount of glandularity, the correction of glandularity based on the image itself and the spectrum, all of these values are based off of, tables. And that's okay. If you have access to these tables, so you go to these publications and you go in, you do your measurements, you know what your air kerma is, you know what your half value layer is, and you know what KV you imaged, your ion chamber and your phantom, you can calculate that. You can take those calculation values. If you're using the Wu and Boone method, that DG sub n, you can take those values, multiply it by the air kerma you measured, and you get mean glandular dose. There's nothing wrong with that. It's just, it's very manual in that regard. It requires looking up values, calculating things. Now you can do this with software, that's fine. But the nice part about the 2ABD is here we go. The 2ABD method has the ability, and I'll make it bigger. It has all of this value, all of these values are built into the DICOM metadata. In this case, all we need to know is the error kerma, which I'll show you on the next slide as a reminder, is something that we can calculate. We don't have to necessarily measure it. And then the mu, which is the attenuation correction, that's a value that is based off KV, MAS, target filter combinations. And then of course the breast thickness, which that's all built into the DICOM headers, all of that. So you get an image that comes up and then you click on the DICOM data, you right click or however you get the DICOM data to appear, you can find all of those values. And those values can then be, if you have software, at the national level or not, it would open up the image, take all the data out, it would do some calculations and spit it out. This process is more aligned with being automated. The other process requires lots and lots of tables that you have to then, you can put those tables in Excel spreadsheets. You can still do the calculations. I'm not saying you can't do those with Woo, Dance, Boon. We've been doing that for something like 30 years now. But this new 2ABD it's more friendly for the way we image because all that data is collected in the DICOM header. And the last part that I think is probably the most important is the 2ABD does not require us to assume glandularity. So we don't have to worry that there really is no such thing as a 50-50 breast out there. We just simply know what KV it was. We know what the MA was. We know which filter target combination there was. We know the breast thickness based on the compression. And we can calculate the error kerma just based off of all of those values. And so if you want, there's a couple of publications, all of my publications that I use for the 2ABD right here, they're all listed here. You can go online and you can read as much as you want about this and how they do the calculations and whatnot. To be frank, if you just Google 2ABD, I'm sure it would all pop up anyway. So it's very easy to learn more about it. But, I stress the fact that this is relatively new. It's in the last couple of years, it's new. Whereas mean glandular dose, D sub G, we've been doing that for 30 something years. And so all of the vendors are very used to reporting mean glandular dose. My guess is in the future, at some point, you might start getting 2ABD options. It would give you the mean glandular dose based off of 2ABD instead of based off of Dance or Boon or Woo method. So that's just my guess. So the standard user, the radiologist, would never see a difference. The dose, the mean glandular dose would just appear, and that just whatever the dose value is would be reported. But the methodology behind the scene may change. And so I just recommend going, and these publications are, like I said, Google 2ABD mammography, and they'll pop up and you can read a lot about them.
Mm-hmm. Yeah. Thank you so much, Sam. I think that is all questions we have for today. But for next week, that we are going, it's like a wrap up things. That we are going to talk about those index registration, where to start. I think we already started that part. And also about the how to interpret all those data. One thing that I'm going to ask you, because I know that every week that we talk about each modality, CT, radiograph, IR, fluoroscopy, mammogram, I know that every week that we talk about those things, you put comments for us for the future or next cycle that we are planning to do things. And maybe it's maybe a good time that we put those things together again as a wrap up. And we can discuss like a point by point on that things, because I know this is like almost 3 months, I think it's 4 months that we talk about this thing. And sometimes we forgot, right? Because a lot of knowledge and a lot of things that I learned from you. So maybe it's maybe a good idea to put those things together again, that, okay, this is your recommendation that we should do for the next cycle, or some questions that you question, and maybe we can answer that things, and for clarifications and for the future that we can do something more. That may be a good session to do so, because next week we're gonna have Dr. Jirapon and Dr. Panuthai joining us, and maybe Naprapong if he available from party. Yeah, he has like a party almost every day, even like it's a COVID time.
He's popular.
He's popular. I cannot blame him. Yeah. Yeah.
No, that'd be great. I'll summarize everything. Obviously, next week everything we're going to talk about next week we've talked about for the last 3 and 4 months, and so we'll just kind of pull it together. We'll give one good presentation. We'll go through all that process. Maybe a little bit of more dialogue. We can go back and forth, and then and if anyone else online has a very specific question they want, I can if I hear about it soon enough in the week, I can address it specifically. If not, I'll just, as you said, I'll summarize everything.
Yeah, and I think it's a good time to like summarize and maybe like wrap up those things, because it's not only benefit for Thai people, but also like people in this region. Like we have the audience from Bhutan, from Vietnam, from Singapore. So it's like a help all of us to start and understand. Okay, if we want to start, what should we have in mind to like for the process and those things.
Sure. So I can answer how should we start if we're starting from nothing, and then I could also talk about next steps, for places like Thailand and a few other like Malaysia and whatnot that have already done some or have gone one cycle. They're going into the second cycle. So we can approach that.
Yeah. I think that's going to be a good things to do, and maybe like a summarize for the main concept from each session that we talk. Yeah. Okay.
It looks like there's another question. Let's see.
So, if patient asks for her dose that she received in her mammogram, what do we need to give her, like an effective dose or granular dose?
Yeah. So that's a tough question, because people always ask me all the time, well, what was my dose? And, in reality, we can't tell them. We don't know what their dose is, but what we can tell them is you say, someone, the dose that the system you gave based on, a woman like you in this population. So I don't know let's say she's a 40-year-old woman, the dose to a typical 40-year-old woman that got an exam just like you would be blah. Now you can tell them your mean glandular dose, but that really doesn't mean a lot, because that doesn't really convey risk. Now you can tell them millisieverts. That's something that you can relate to. So if you say 0.3 millisieverts, well, that makes a little bit, you can now say, okay, well, 0.3 millisieverts, that's a third of for us in the US, that's a third of our annual dose. So that's like getting 3 months of radiation. Just you live and breathe 3 months of radiation. That's the same of you getting that. And so it kind of helps them put that into perspective. Obviously it's going to be different for where, Thailand, your guys' average values are lower. So it might 0.3, I think, is actually an annual dose for you guys. And so it might sound like a lot. And so it's always difficult when you compare it, because sometimes it scares people no matter how you share the numbers. The thing I always tell people when they get this is I always say, think of it this way. We're here imaging. I mean, why are you here? You're here to make sure you don't have cancer. Okay. Do you feel good that you don't have cancer? Yes. Okay. Well, then, the benefit for this was great. Now, the worst case scenario is if we do find a cancer, if we find it while it's early enough, we can treat it. And almost all cancers, breast and other, if we find that cancer early enough, most cancers are treatable. And so that is why you're here, because we want to make sure you live a long and healthy life. I know 0.3 millisieverts may sound like a lot and it might seem scary, but if you compare the benefit to the risk of what's happening, then you'll realize that receiving this exam so that you don't have cancer should give you a lot greater peace of mind. So I always try to talk them through why they're getting their treatment instead of just give them numbers. But in the end, I would probably do effective dose.
When you compare with like the natural background, that may be a good idea, because you still get things anywhere.
Yeah, I mean, you I mean, like I said, 0.3 is kind of high if you sit. I mean, when someone comes in and gets a CT and we say, oh, that's equivalent to 1 or 2 years of background radiation, they're like, oh my gosh, that's a lot, because it's 1 or 2 years. It sounds like a lot. In the end, it doesn't mean anything. You'll live 1 or 2 years and you'll never think twice about your
True.
risk of background radiation. You just never
That's
think about
true,
that.
yeah. Or maybe like if you have cancer and you did not get a CT, you're gonna maybe pass away in 3 months.
Yeah.
Instead,
yeah.
Yeah.
Yeah. And that's exactly what it is. If you say, but if you get cancer and we don't catch it early enough, the chances of you dying goes
Yeah.
through the roof.
Yeah. And how about if we compare, or if we tell the patient on the dose that they get compare with the DRL, is that a good way to do that? Or
Yeah. I mean, that's definitely something you can say. You can say, the doses we use on this machine itself are at or lower than all the doses in the nation. So, you should feel comfortable if you get imaged here or, anywhere, you should know that you're getting on average a reasonable amount of radiation. And but they might not understand that, but what you say is, hey, we have this standard. And what we're trying to do here is make sure everyone gets the right amount of radiation for their imaging. And so we make sure that these machines don't overexpose. And we are trying to we're keeping the dose as low as possible. And sometimes all you have to do is say that we measure these machines, we test these machines, we're constantly making sure these machines are, perfectly optimized. And they don't necessarily need to know how you do it, but that sometimes makes people feel good.
Yep. Sure, sounds good. So thank you so much, Sam, for the lectures, and we have a really productive discussion today, and it's very practical for us to understand the basic concept on the mammogram, which initially I thought, oh, it's probably not that difficult or complex, but turned out it's more complex than I thought.
Yeah.
The mammogram, because like a lot of like fine details on things. Yeah.
Yeah, you think it's so simple. You're imaging one thing, right? One thing, the breast.
One thing, and also just calcification to call like a microcalcification for malignancy or not, but no.
Yep.
There's like a multiple consideration. Yeah.
Yeah, I mean, it's amazing what we can do with mammography. It's one of the few imaging modalities out there, like I said, that we image quite literally one thing, the breast. But yet it is so very complex because the breast is very hard to image. There's only two real things you're imaging, glandular and fat, but because they're the tumor itself is so close in attenuation to the glandular material. Yeah. Anyway, it's fun. That's why I like physics.
Yeah. So thank you so much. And as always, so after this session for the audience, you will get a link for evaluation. So please complete the evaluation by the Thursday midnight. And on Friday, you will get the certifications. And on Friday, you will get a link for the last session, wrap-up session for next week. And if you have any questions or something that you want Sam, Dr. Brady to speak or to talk about, you can comment on the Facebook Live, on the comments, or you can send an email to me. Maybe like before Wednesday. So if you have not heard anything before Wednesday, so that all of your homework that I just told you, right? Yeah. Okay. So thank you so much, everyone. And also thank you everyone for attending these lectures, almost 4 months. Next week, we're going to do one more thing. So normally for the mission, we take a photo every time after the mission, but this time it's like an on-site mission. So we still take a photo. So make sure that you have like really nice makeup or something. And at the end of the lectures, we're gonna ask you guys to open your camera so we can take a group photo to show that this is a complete mission for us. So thank you so much, everyone, and have a good night. สวัสดีค่ะ Bye bye. Thank you. ค่ะ